Graphite Demolder team. This is Nick, this is Michael, and Anthony. Our sponsor is CPS Technologies, and our advisor is Dr. Wendy. CPS Technologies is a world leader in metal matrix composite. They combine metal and ceramic materials into one to make a very resourceful material. And the aluminum silicon carbide is one of their main materials that they use for almost all their products. And one of the main products that we are working with is the aluminum silicon pin cooler. And that it has a lot of applications, especially in cars, like the electric cars. The power modules in the electric cars, this is what basically keeps it cool when it's running, and also the power modules for restoring energy when you brake in cars. It basically redirects the energy from the car. And the main problem that they are having is the fact that the pin, this is the aluminum silicon carbide, the pin cooler. The problem is that due to the coefficient of thermal expansion, when it's exposed to high temperatures, the expansion of the aluminum silicon carbide becomes extremely bonded with the graphite mold, which makes it very difficult to take out after it cooled down to room temperature. So our task is to basically come up with an idea to extract the part without having this crack. And I am the team leader, and I'm responsible for giving everybody the task, what to do, how to stay on task, make sure their responsibility is on point. And Nick and Tony were the main men for working with the manufacturing part of the machine and making sure that everything at the end was working perfectly well the way our client wants it. And me and Gonzo worked with the research while also helping with the SolidWorks simulation and design of the machine. So I'm going to pass the mic to Tony to give you more details about the device.
So this is basically a continuation of last year's design, and I want to showcase last year's design that included an actuator, a vacuum brick, 2 clamps, and then a very important aspect of that design that was primarily the way that it demolded the parts was a concave base that under the clamping forces would essentially separate the part from the graphite mold. And from the starting point, we decided to start testing that design to see any improvements that we could come up with. And the first one, as you can see maybe in this picture, is the hoses that were being used here and here were caving in on themselves. So one main improvement that we thought of was improving the hoses. In this next design, we looked at the clamping forces that Nick rendered, and through our research and data collection, we basically came up with an average of 50% breakage rate. So we tested, I think it was an initial of 10 parts, and out of those 10 parts, only 5 came out of demolding without breakage. And to add furthermore into that, those 5 parts took a random number of times for the actuator to actually pull it out of the mold. So CPS couldn't really implement it into the manufacturing process because it wasn't efficient with its time consumption. Another problem that we surfaced was the actual seal at the vacuum chuck, at the top of the suction, it was a custom rubber seal that was grooved into the CNC brick, but it lost suction power because it wasn't fully sealing the orifice. So that was another design problem that we faced. So this is the naked frame that includes a new surface area that Dan, the machinist, Paul, helped us take away from the concave, because as we clamped down the graphite, it was actually breaking instantly, and so we decided to completely get rid of that, keep the same frame, and now I will give it over to Nick to explain any changes we made to it.
So I'm going to take a step back from this before I talk about it and talk about the first semester. We ran 10 tests initially, then we ran another 20, and we kept finding that the curvature on the plate was breaking the molds more than anything else. And when they weren't breaking, the vacuum wasn't pulling them out. We would either lose seal because the parts are dirty when they come out, or it just wasn't strong enough. From there, we had meetings with our advisor, and at one point, he talked about us implementing vibration into the system. This was kind of a huge turning point for us, but it was late in the semester. So over winter break, we took a few parts to my house, and my father has a big shop, and he uses air hammers pretty much for anything mechanical. And just out of that thought, we tried using the air hammer on the parts to remove the parts from the mold. And it actually ended up working out really well. The only problem with that was the air hammer surface area is so small that we were damaging some of the parts on the surface. So then from there, we spent a lot of time researching anything that we could use to run the same vibrations per minute and the similar force that the air hammer was making. From there, we talked to Don Foster, and he showed us these piston air hammers, or piston air vibrators, that actually the MasterCard had. From there, I did more research and found Vibeco, and they were very, very gracious to help us with our project. I guess they've worked with other senior design projects before, and it was really easy because they were located in Rhode Island. So this right here is the pneumatic piston vibrator. It has just a piston inside that vibrates up and down and creates a vibrational force on the surface of the part. This is good too because this had a greater surface area, and once we started testing with it, it completely eliminated any damages to the part. And like Tony said, we deleted the curvature plate, the deflection plate that was causing the breakage when we were bolting parts into the machine. So we went with this method. Also, they provided us with the oil lubricator to keep this lubricated as the air pressure's on, and an air pressure regulator to make sure that the air pressure stays consistent when we take it from testing here to testing at CPS. So this is our prototype design that we actually went with. Like Tony said, we kept the original framework, and the funny thing was I brought a design to CPS, and it was a completely different system, completely different frameworking, and they looked at it and they suggested that we just use the original frame, and it kind of just clicked from there. So here's the linear actuator that we kept from last year and the framework that we kept. We deleted the plate that was down here that deflected the molds and broke them, and then we had to just have a couple parts machined to make it actually work together. This is the first one that we had to make. This is the vibrator adapter that we used to adapt the vibrator to the linear actuator. This gave it the capability to move up and down away from the part. This is the slotted adapter that we had to make. This was huge too because before the linear actuator was only in one spot and was not able to move left or right horizontally on the part, which is very important to what we did when we first tested with an air hammer. The air hammer, we were testing with the part, we'd vibrate the left side and you could instantly see the right side pop up out of the mold, and then we'd do the opposite and the part would break free. So this is the actual adapter bolted to the crossbar, top crossbar of the framework, and we actually had a problem there when we first finished it. We went to bolt it in and realized that bolts were going to be sticking down a little bit into this area. I'd like to thank Paul for just coming up with the idea of he chamfered the bolts, or all the holes, so we could use a flush bolt system for that. And this is the actual two machines side by side where we can see the main differences. So this was their whole vacuum system that was used to pull the parts out of the mold. And then, like I said, they had the curvature of the plate that bent the mold. And we learned really fast that bending graphite didn't go very well. We were just breaking parts too often, and that was the overall goal of our project, was to not break them. So by eliminating that and then applying pressure and vacuum force, or vacuum frequency on the parts, things went a lot better from there. So first, for our experimental testing, when we got the vibrators, we used them manually with an air line and a few drops of oil, and while they did remove the parts from the molds perfectly without any damage or any breakage, it was really hard to do, but that was mostly because all the vibrational frequency was going right through my arms. And another thing I'd like to touch on was the frequency. So we were running around 40 psi, so it gives you this 4,000 vibrations per minute. And that was actually when I contacted Snap-on, just a little higher than the air hammers that we were using. Obviously, those air hammers create a lot more impact force than this does because it's just a piston moving up and down. So that kind of also eliminated the problems of us ruining anything. Along with that, once we actually built everything and hooked it up, you could turn the vibrator on for almost a second or two, and it would instantly pop one side of the part out of the mold. And that allowed us just to easily and quickly get the parts out of the mold without damaging anything. I'm going to hand it off to Keston with some simulation results.
One of the main problems we experienced was trying to run a simulation on SolidWorks before we moved on to actually implement the pneumatic piston to incorporate vibration into the part. The main problem, as you can see, is that there was too many constraints to try to apply to the mold itself without interfering too much. If you can see the constraint that we tried to apply on the mold itself. Ideally, we wanted to use the same area on the clamps where it shows on the where we clamp the part down in the actual machine, but unfortunately, it didn't want to take it. So we decided to go to the next best thing, which was this. We came up with some values, but again, due to the complexity of the actual part itself, the numbers just did not come. It didn't fit too well with what we wanted. Pay attention to the middle part is the natural frequency we found for the pin-fin part. We figured it would be better to at least have an idea of what it's going to look like before running the test we want, even though it's not completely accurate to what we are looking for. Moving from a static simulation to a dynamic simulation, it definitely requires more computational capacity, which we just did not have. But with this, we were able to at least have for confidence that yes, we can definitely go on and it will be fun. Plus, we had the backing of our client that the complexity of the pin-fin part would definitely hold up to whatever vibrational force we add to it and not affect the part or its application at all. So I'm going to end the mic to Michael on the timeline and budget.
So as of early last semester, this is before winter vacation, our plan was to just replace the vacuum hose and other parts that came with last year's design system. Due to cost efficiency and wanting the system to work effectively, and also some research, we decided to switch from that plan and go with the piston vibration plan, which set us back a little bit, but we were able to get on track with our time and scheduling. Our initial budget was $1,000. As you can see, we came below $1,000 budget, which is a good thing on our part and also on the company's part. Before we came up with the piston vibrated idea, we actually had a sit-in with our client, which is the company CPS Technologies, and we brought it up to them. And the advice they gave to us was to just find ways and means to implement the piston vibrator idea into the system. We also spoke to our advisor, and he also told us the only way we can actually see and work properly, efficiently, is to try an error process. So that is exactly what we did. So this is a video of how our system works. You can see he moves it to the right side and he drops the piston vibrator and he vibrates the right side, and he switches it back to the left side and he drops it and vibrates the part. After vibrating, he just unclamps it, take it out, shakes it a little bit, and the piece just comes up by itself. Looking at this video, we were able to run 60 parts through the system, and we only had 4 breakages, which is the last end. And we were able to also save time and also save some sort of money for the company. Also, things we would like to improve is possibly find an automation for the machine, which is try to find ways and means to take more pieces apart at once, and also see if we can cut down most of the time, because it only took 30 seconds to actually take one part. So I think we can try and cut down that's 30 seconds to at least 20 seconds. We also think we will be able to change the single linear actuator to a double linear actuator, because the single linear actuator just goes up and down, and the double linear actuator goes up and down and left and right. So as you saw in the video, he manually moved the actuator from the left side to the right side, from the right side to the left side, which with the double linear actuator he wouldn't have to use that manpower. It will be done by itself. I'll hand it over to Carsten so he can use that technology.
Before that, I would like to point out that based on the idea we had during the beginning, when we came up with the vibration idea, we thought that if we could incorporate the vacuum portion from previous year to this, it would make it a lot easier to remove any manual part or action required by anybody. Because once the vibrator to the loose and it's an automated system, the vacuum can easily just pull it right out, which would probably save even more time. And with the acknowledgement, I would like to thank my advisor, Dr. Wenzen, Professor Foster, for giving us great ideas on what to do and where to head in the right direction. Obviously, Paul, thank you for the machine. Taught us some great stuff. Sue, and you're definitely one of the backbones of the MD department. We thank you too. And obviously the judges probably have busy schedules. We want to also thank you for being here. And CPS Technology, thank you for giving us the project. You guys are awesome. So we'd like to ask if you have any questions.
Yeah, we have very tight schedule too, okay?